Now, in terms of our GLM, then we still have the time series of our voxel right here. And now in our design matrix, we have two regressors. One is our canonical, and one is the temporal derivative. Notice, however, that now we have two parameters. And this makes it a little bit harder to interpret. For example, what if the difference between condition A and condition B across your group were in the second parameter, in the temporal derivative? How exactly would you interpret it? Right? It gets a little bit harder to interpret. It also gets harder to aggregate at the second level. Because now we have two parameters, how do we put them together? On top of that, if you've ever done an fMRI analysis, you know that the conventional thing to do is actually to discard entirely, after the first level analysis, beta 2, and to only carry forward to the next analysis beta 1. And this, of course, is silly, even though everybody does it. It's silly. Imagine that there are two participants with the exact same amplitude of response to your stimulation, except participant A, their HRF is perfectly canonical, is exactly the canonical. So for them, all of the amplitude of the response will be allocated to regressor 1, to the canonical. Now, participant B, on the other hand, has the exact same magnitude of response, but their response is much faster. So happens quicker in time. So mismatches the canonical. This means that part of that amplitude will be taken away from the canonical and will be given to the temporal derivative, so that together they can sort of adjust to that faster HRF. As a consequence, we've taken away amplitude from the canonical, and we've given it to the derivative. So if now we throw away the derivative and the beta 2, we're essentially penalizing subject B just because their HRF doesn't match the canonical. And indeed, somebody has worked out a way where you would still be able to use and recover the amplitude that was allocated in the second regressor, so that you would carry forward sort of an aggregation of these two regressors. But somehow that approach just hasn't stuck. And of course, you can keep playing this game. You can keep expanding the number of basis functions. So for example, instead of just having the canonical in red and the temporal derivative or the first derivative in blue, you could have the three basis functions. You can have the canonical, the first derivative, and also the second derivative, also known as the dispersion or spatial derivative. And now if somebody happens to have a wider or a narrower HRF, you can use the second derivative in order to adjust for that, which is wonderful because it gives us more flexibility to better match the HRF of this one particular participant. However, now we have three parameters, right? So this is what it would look like. Again, our canonical, first derivative, second derivative. And as you see, now we have three parameters, which makes it harder to bring them forward at the second level and aggregate them. What does it mean if condition A and condition B differ in beta 3? How would you interpret that? Right? It's difficult to interpret. On top of it, as I said earlier, typically people forget about beta 2 and beta 3 and only carry forward beta 1. So again, yes, we're better matching one participant's HRF, but we're still penalizing participants for, quote unquote, having the wrong HRF. And then you can sort of, at this point, you can just start using several different models. For example, you could use just a Gaussian basis function set. So where you have three Gaussians, and again, now you would still have three parameters. FSL gives you the ability to use what they call a constrained basis basis set, also known as FLOBs, that's the name of the tool. But the idea is that with just these 5 functions that you see right here, by putting them together, again, a bit like a cake, in different quantities, you can create virtually any of these shapes right here. And the reason why they picked these 5 ones is because overall, this set of shapes right here is the set of likely shapes of HRF that people have. So in a sense, they constrained the set of basis functions to what is plausible in the domain of hemodynamic responses. Look, the hemodynamic response is not going to go down and then zigzag up and down in straight lines. It's going to be something like one of these. And so FSL just thought, look, we can use these 5 functions. In fact, you could even use 3 and approximate pretty well most HRFs. So for example, this is one example with 3. So you have one that kind of looks like a canonical, and then you have these other 2 functions. And together, they give you great flexibility in modeling precisely somebody's HRF. The problem is that, yet again, you're left with 3 or more parameters. And again, they're hard to interpret. It would be pretty hard to tell what does it mean if condition A and condition B across your group of participants were different in this regressor right here, or in this regressor right here. And on top of it, as I said, it's then difficult to aggregate these at the group level. How to evaluate in a group level fashion is not obvious. And finally, perhaps the ultimate flexibility comes from what is known as a finite impulse response. And this is literally the idea that we're going to have one regressor per each volume that we acquire during a stimulation. So for example, let's say that our block lasts 32 seconds. Right? We'll have one regressor for time point for volume number 1, then one for volume number 2, one for volume number 3, 4, 5, 6, et cetera, et cetera, et cetera. So now we're going to have as many regressors as volumes that we want to model during stimulation. To show it in terms of our GLM, it would look like this. See, for example, we have 1 trial, 2 trials, 3 trials, and 4 trials. And for each trial, we have 1, 2, 3, 4, 5, 6, 7 regressors, each of which, so the first one is capturing the amplitude of the bold response in volume 1 of trial 1, and then volume 1 of trial 2, and then volume 1 of trial 3, and then volume 1 of trial 4. And then the second regressor will code for volume 2 of trial 1, volume 2 of trial 2, volume 2 of trial 3, et cetera, et cetera. So now, essentially what we're doing is we're averaging every individual volume. And what we end up with is known as a tent function, right? Every volume has its own amplitude. And then you can connect it to get the response. And I'll show that in a second. However, the problem is that now we get 7 parameters, 1 per each of the regressors. So imagine that we do our task. What does it mean if the difference that we find between task A and task B is in the first, the third, and the 7th beta? What does that mean? It's not obvious to interpret. So let me bring all this together. So we've seen that sort of there's really a continuum of ways in which you can model the hemodynamic response function. You can start with the so-called canonical, which is a single function that captures or prescribes how somebody's HRF should look like. And everything about it is fixed. The only thing that has to be estimated is its amplitude. And then we can make this more and more sophisticated. We can use the canonical with 1 or 2, the first or second, and the second derivative. And or we can use sort of higher numbers of basis functions. Now, in terms of the basis functions approach, so again, the HRF plus derivatives, the constrained basis functions, or perhaps the finite impulse response, obviously the positives of it is that it gives you much greater flexibility in better adapting the estimation to one particular patient's HRF. And it gives it the ability to vary and to capture that variation. So you can capture, unexpected shapes, something that just doesn't look like the canonical HRF. In this sense, you're much less biased to only find responses that look like your canonical HRF. So you will also be able to detect participants who have unexpected HRFs. And the degree to which you're less biased is FIR being the least biased of them all, and then all the way up to the HRF plus the derivatives. Now, on the other hand, however, you do get much greater variance because things can vary in so many ways that you end up getting much more variance. And you can partition the variance, somebody's response, into so many different functions that you typically end up with a lot of variance. On top of that, instead of having one parameter, easy to interpret, easy to aggregate at a group level, you now have 2, 3, 5, 7, 10 parameters. And it's not easy to integrate them in higher level analysis. So finally, sort of to bring this together, the problem is the usual problem of bias variance trade-off, as always in statistics. You can either assume that you know how somebody's shape looks like, and if you do that, you're biased, but typically you get less variance. Or you can say, let's estimate it. Let's go in and see what somebody's brain shape, HRF shape is. But that will also introduce a lot more variance. You're less biased, but it'll introduce much more variance. Either way, mismodeling people's HRF will increase the noise in your analysis and in your inference. And to give an example, this is a canonical HRF. Yes, there can be variance to see exactly how much this increases at each volume can vary a little bit, as you can see from these error bars, but not that much. Compare that to, I'm sorry, it's a bad picture, but this is an FIR. Here we're literally just averaging all the first volumes and all the second volumes and all the third volumes and all the fourth volumes, et cetera, in our task. And you can see how much variability this could have. And so really here it's a bit of you have to sort of delicately try to pick a good middle between being too biased, but with little variance, or very little biased, but also with a lot of variance.